to be able to begin with the dual simplex algorithm or the primal dual, we need a dual feasible solution. So, I will tell you how to do it. So, now let us talk about how to obtain. So, yeah, okay, how to obtain, and we can begin from here only. How to obtain a starting dual feasible solution. Okay, fine. So, suppose I have a basis, suppose B is a basis which is neither a primal feasible or dual feasible. Okay. Let me make a tableau representation. So, here and assume, or we will just assume that the first, just because it makes the representation of the tableau very simple, assume that the first m variables are basic. Okay. So, then my tableau would be like x1 to xm and then xm and xm plus 1 to xn, which includes slacks plus everything, right. So, here you have, it is all 0 zeros, because the basic feasible, they are in the basis, these m variables. Then you have Cm plus 1 minus Zm plus 1 and so on up to Cn minus Zn. Okay. And this is your right hand side, right, whatever the value of Z. Okay. So, this is a matrix which is I here. Here you have your y m plus 1 and so on, y n, and you have your b bar. Now, since the basis, the current basis is neither primal feasible nor dual feasible, there are some entries here which are less than 0, strictly less than 0, and there are some entries here which are also negative, right. So, what we are saying is that add the constraint summation x j, j varying from m plus 1 to n less than or equal to m, m a large positive number. Okay, a sufficiently large number, and it will be clear how sufficient. So, if you add this constraint, then you will add a slack variable here. So, that becomes plus x n plus 1 is equal to m. So, let me add this constraint. So, this will be all zeros here, this is 1 1 1, and then I am adding. So, let me just make room for x n plus 1. Right now, this is 0. So, this is 1 and it is all zeros, right. This is m here, this is your z, and this is your b bar. So, this is my new tableau representation of after adding that constraint. Now, what we will do is, I want to obtain dual feasibility. So, what I will do is pivot on k, where, or pivot on a k, or sorry, again it is not a k, it is actually y k. Pivot on y k, where k corresponds to, where c k minus z k is minimum of c j minus z j, overall j, and obviously the negative ones will only figure here, right, and this is less than 0. Since there are at least one entry which is negative here, so the minimum will occur for the negative one, right. So, if there are more than one, you select the one which is the smallest, right. And then, so let us see here you have C k minus Z k, and then I will pivot on this entry here, which is 1. This is 1 and then this is y k, because we want to remove this from the basis. So, we will pivot on this one. So, pivot on in fact, I should say pivot on, let me make this more clear, pivot on y 0 k, where I am calling this the 0th row. Oh, without any confusion, just to write it there, but actually you are pivoting on this one, right. So, when you pivot on this one, to make a 0 here, you will multiply this row by C k minus Z k, right, and subtract. So, when you so because it is the smallest one, when you subtract from here, this will become, everything will become non-negative. Is that clear? Because I am subtracting the smallest number from among all these numbers. So, when I subtract it, it will make everything non-negative, right. So, whatever the bars here, you can write them as bar, and this will all become non-negative. So, this will be 0 and this is bar, this is bar here, and then this will become minus of, okay, maybe there is not here, I will write it here, this will be minus of C k minus Z k, which is also non-negative, which is positive, right. And then you will again do the same thing. So, here yeah, so now yes, yeah, let me give you all the steps here. So, actually you have dual feasibility, you do not have primal feasibility. So, we have obtained a dual feasible solution. So, now the new the extended basis is dual feasible, right, because you have non-negativity here, you have a basic solution, right, primal feasibility. So, one can begin where one can either, so once we can now proceed with either dual simplex algorithm or primal dual. Right. Once you have a starting dual feasible solution, you can begin either the primal dual or the dual simplex algorithm, right. Okay. But remember, you have a different problem, because you have added a constraint, and so you have a one more, your basis size is extended. Okay. So, let us see what are the possible outcomes. When I suppose I start with dual simplex or primal dual, what are the possible outcomes? First is that dual is unbounded. Yes, by now, if you have solved enough problems and you have understood the presentations here, you will understand that adding this constraint has nothing to do with dual unboundedness, right, because the dual unboundedness will mean that here you have a negative entry and everything in this row is less than or equal to is greater than or equal to 0. So, that you cannot proceed with the dual simplex algorithm, for example. So, therefore, the dual problem can be unbounded, right, dual is unbounded, which implies primal is infeasible. Okay. Then you have obtained an optimal solution, that means your algorithm has ended, and what are the possibilities? Optimal solution is obtained with xn plus 1, and let me call it star greater than 0, where I am referring to this star as the optimal solution. The stars. So, suppose xn plus star, xn plus 1 star is greater than 0. What would that mean? That here, if this is positive, it is in the basis. So, therefore, the constraint is not satisfied as equality, and so the new constraint is not binding, right. The new constraint is not binding. So, it was just a device, and by the way, add the constraint when we say this is also known as the artificial what am I writing, artificial constraint method to obtain a starting feasible solution. Okay. So, this constraint is not binding, and therefore, I can drop the this implies that the new constraint is not binding, right. Therefore, x n plus 1 star, therefore, the column and row corresponding to x n plus 1 star can be dropped from the tableau. Okay. And whatever you have is your tableau corresponding to the original problem, and so you have an optimal solution for the original problem, right. Now, what it can be the third one, that optimal solution is obtained with x n plus 1 star equal to 0. So, that means the status of x n plus 1 star is either basic or non basic, but it is at 0 level, and that is what we are concerned with. It is not important to know what the status of x n plus 1 star is, as long as it is 0, right. But the only thing is that if it is 0, again two things are possible. Yeah, okay. It is important that even this discussion, we may not be able to do it right up to the end, because some loose end may be left out, but does not matter. Let us see how long you can follow, and I will just spend as much time as I feel it is necessary, and then you can always read up some more, or you can sit down and work out the details. But anyway, optimal solution is obtained with x n plus 1 star 0. Now, if so, this is case 1, if the objective function value depends on m, as is a function of m. See, we do not know at the final tableau, this is equal to 0, and if the objective function value depends on m, then the objective function value can be decreased. Now, let us see, if we are solving the dual problem, it will have to be increased, right, and maybe we can be increased CREA can be increased. Well, at optimality, what is happening is that the two objective function values are the same, the primal and the dual are the same. So, you can, okay, we will have to come back to it maybe, and the objective function value can be increased as m goes to infinity, but that will not be proper. So, okay, I will tell you why did I argue that this should not be increased, because you see, once we have obtained an optimal solution here, then my primal is feasible, because x n plus 1 star is 0. So, I will bet for decreased, and then we will come back, can be decreased as m goes to infinity, right. As m goes to infinity, this will imply that primal is unbounded. fine. And if so, the second case would be that if the objective function value does not depend on M. But the thing is that since the constraint is binding, the objective function value does not depend on M, but the basic variables do. Variables depend on M. Fine. And yeah, you might say that okay, it's not very clear, so we will come back to it sometime. But again, you need a little more familiarity with the simplex algorithm. In any case, see what is happening is that if the objective function value does not depend on M, but the basic variables may depend on M, because the constraint is binding, therefore what we can do is we can reduce, yeah, so let me write it out here, we can reduce the value of M. So in this case, I am arguing about 2, so I am saying that reduce the value of M till one of the basic variables, or maybe more basic variables becomes 0, because the constraint, so the constraint is binding. So till one of the basic variables becomes okay, you have to reduce the value of M till the till all the basic variables remain greater than or equal to 0. Okay. Say for example, if you have the value M minus 6, then you can reduce M up to 6, because after that, so obviously that means that one of the basic variables will become 0, right. So that's the smallest till you can go, and the new solutions you have, and therefore the reduced solution. So you will fix the value of M like that, and then what you will have will be independent of M. So the reduced solution is independent of M and solves the original problem. Yeah. So this is quite interesting, and it is maybe in the assignment sheet. What I'll do is I'll try to give you numerical problems which cover all these cases. I'll be able to cover one right now, and then the other ones I'll give them as exercises, and hopefully, and so by that time I will also have solved them, and then we can check whether these outcomes become meaningful. Okay. Thirdly, let me just show you what we mean by this, that if the objective function value, the optimal solution is obtained with x n plus 1 star equal to 0, and the objective function value depends on M, then the objective function value can be decreased. Yeah, okay. The idea here is, suppose a simple example. So here we are saying that the objective function value depends on M, the objective function value can be decreased. See, the thing is that you may be at this point, and this is your artificial constraint, right, which corresponds to your M. So this is your point. The thing is that since you are minimizing your, this thing is decreasing in this direction. So if I further increase the constraint, that means it will move parallelly to itself. So then this will become the new optimal solution, which will reduce the value of the objective function further, and so on. So I can go on, I can go on increasing my n, and correspondingly the objective function value will decrease. This is the idea, right? Okay. So and other things. So hopefully I should be able to give you some numerical examples on which you can work out. So here I will just show you this one. If you look at this example, the example is minimize z equal to 2x1 minus 4x2 minus x3 plus 2x4 minus 3x5 subject to x1 plus x2 plus x3 plus 3x4 plus x5 plus x6 is equal to 6, and the second constraint is x1 plus x2 minus 2x3 minus x4 plus x5 plus x7 is equal to minus 3, and xj greater than or equal to 0 for all j. So, let us write the dual here. The dual would be maximize psi equal to 6, okay, 6y1 minus 3y2 subject to y1 plus y2 less than or equal to 2, y1 plus y2 less than or equal to minus 4. Okay, that's okay. Then y1 minus 2y2 less than or equal to minus 1, 3y1 minus y2 less than or equal to 2, and y1 plus y2 less than or equal to minus 3. Yeah, and finally, with respect to this, you have okay, y1 y2 less than or equal to 0. Okay. So, in any case, if I choose choose the basis, B as your A6 and A7, which is E1, E2, right. Then that basis gives you the feasible solution, the basic solution as x6 equal to 6, x7 equal to minus 3, and you can see that from the top, because the entries are not all non-negative, so it is also not dual feasible. So, this basis is neither, so B, this not neither primal feasible nor dual feasible. Okay. So, we need to have a starting dual feasible solution, and we will use the artificial constraint technique. I will have this as x1, x2, x3, x4, x5, x6, x7 and x8. So, I am going to write that right away, okay? And which will x8 will correspond to the constraint. So, here this is 2, 1, no, 2 minus 4, 2 minus 4, yeah, minus 1, 2 minus 3, minus 1, 2, minus 3, 0, 0, this is 0. So, this is right now 0, and this is 1, 1. So, because our basis corresponds to x6 and x7, so the artificial constraint that I will add will be 0, 0 and 1 here, right. You are adding a slack variable x8, and then this is m, very large number, right. Now, you write down the constraints, which are 1, 1, 1, 1, 1 minus 2. Achha, I shouldn't have written this. This is not needed, because I am treating this as a constraint. So, it is not needed. 1 minus 2, 3 minus 1, 1 1, 1 0, 0 1, 0 0, and this is 6 and minus 3. So, right now the basis is neither primal feasible nor dual feasible. Right. So, the first iteration here we will look for the most negative, because I am doing the dual simplex algorithm. You have say that this basis shows you that it is neither dual feasible nor primal feasible. So, you see that this is your outgoing variable, and therefore, and then you choose, because this is the most negative. So, we will pivot on, and of course, the pivoting element would be, oh okay, sorry, here we are not talking, I have inserted this as the artificial constraint. So, we will pivot on the most negative. In this row, we will pivot on the element corresponding to the most negative Cj minus Zj, so that I first maintain dual feasibility. Remember, the idea is to get a starting dual basic feasible solution. So, when I pivot on this, that means I add 4 times this to the top row, and that will give you, this will be 6, 0, 4 times this is 3, 4 times this is 6, 4 minus 3 is 1, and then this is all zeros, this becomes 4, this was 0 here, and the objective function value is 4m. So, now you have a basis which is consisting of x2 in the basis, and then sorry, this is okay, x6 is in the basis. I started with x6 and x7, and that basis was neither primal feasible nor dual feasible. So, now I added this artificial constraint. We remove x8 because x8 was the starting. So, initially your basis consisted of x8, x6 and x7. Now, I have replaced x8 by x2. So, your current basis is consisting of the basic variables x2, x6 and x7, and you see that the basis, that means the columns a2, a6 and a7, this basis is dual feasible, but not primal feasible, because you have m is a very large number. So, both these entries are negative, and because we are using Bland's anti-cycling rules. So, I will let this variable be the first variable to leave the basis, and then you have to apply dual simplex. So, you look for a negative entry here, and this will be the pivoting element, because this is the only a negative entry. So, there is no need to take ratios. So, now when I pivot on this, I have to make a 0 here. So, 4 times we add this row to the top row, right, and then we will make zeros here. So, this table will show you the corresponding calculations. So, here when you make 1 here, and then you are adding 4 times this to the top row, right, and so that becomes, you can just verify that these numbers do not change, but this is 4 times minus 8. So, you are adding to you are multiplying this by 4 and adding to the top row. So, let us just make sure, okay, yeah, this is fine, 8 times plus 6, 14. So, the calculations are okay, and then I will multiply this row by minus 1, right, because it is a pivot entry, pivot element, and then, or maybe you can first add this to this and subtract this from here, and then multiply the row by minus sign. So, get the, so therefore, this shows you the next set of the next iteration tableau, and you can see that here, yes. So, now you have only one variable which is negative, and dual feasibility is maintained because I am using dual simplex algorithm. Okay. So, this is the outgoing variable, and we look for negative entries here. So, the ratio here is 1, here the ratio is 14 by minus 4, which is 7, minus 7 by 2, and here it will be minus 4. So, you choose the maximum ratio, and therefore, this is your pivot element. Yes, and you can see that in the next iteration I am making this as 1 and all other entries 0. So, you will add this to the top row just to get the 0 here, which will give you this again, and you get the objective function value as 15. Remember, yes. So, 3 times you just add this to the top row, and then make a 0, or you can then divide this by -3 to get a 1, and then you subtract this row from here to get the corresponding entries. And now you see that at this point, so at this point this is positive, because m is a large number, this is positive and this is positive. So we have obtained an optimal solution, and the optimal basis is A2, see A2 and then A8 and A3, okay, A2, A8 and A3. So this is the optimal basis, and x8 is equal to, the value of x8 is m minus 6, which means it is positive because m is being taken as a very large number. So that means when x8 is positive, that means the artificial constraint is not binding. Remember, we had added an artificial constraint to obtain a starting dual feasible solution, but now we realize that since in the optimal solution x8 is at positive level, the artificial constraint is not binding. It will be satisfied with the strict inequality if you remove x8, right. So that means, therefore, we can drop the column and the row corresponding to x8 in the last tableau can be dropped from the basis, because we do not need it anymore, right. And so the solution to the original problem will therefore be with this a 7-dimensional vector, and this is your this is obviously a yeah. So now, because you have 2 constraints in the original problem, so therefore this is a basic feasible solution and it is non-degenerate, right. Now, of course, see here, while because we were applying the dual simplex algorithm, it is possible that you may encounter at some intermediate situation that the dual is unbounded. And remember, the dual unbounded means that the augmented problem, because you added an artificial constraint, the augmented primal is infeasible. And now I will like you to think about it, why I can conclude therefore that the original primal is also infeasible. And therefore, we will not proceed any further, because the moment while doing this you encounter that the dual problem is unbounded, you can then conclude that the original problem is infeasible, and therefore stop there, right. Now, there are 2 cases. So, I have discussed the case when x8 is positive. Now, suppose in the optimal solution 2 other cases are possible. Two other cases are possible. I mean sub cases, which is when x8 is 0. So, one condition, one possibility is that x8 is not in the basis. I mean, these are pathological cases, but one should know, because once you have added a constraint, you should know how to treat x8 in all possible situations. So, either x8 is not in the basis because it is at 0 level, or x8 is in the basis. So, now what I will do is, through the assignment sheet, I will try to set problems in the assignment in which either this or this happens, and then hopefully give you a hint how to handle this, because we want to be sure that we know when either this case happens or this case happens, we know how to treat it. I mean, when x8 is not in the basis and when x8 is in the basis. So, not difficult situations, but this now gives you one method to obtain a starting dual feasible solution, and then you can begin with the dual simplex algorithm. And this will have, because you need a dual starting dual feasible solution for the dual simplex algorithm and for the primal dual. So, in either case, you now have a method for obtaining a starting dual feasible solution. Let me show you now interesting application of the primal dual algorithm or the primal dual formulation. See, this is the shortest path problem. The idea here is that you are given a directed graph, and I will explain directed graph G, V and E. So, the usual notation is that you have a set of vertices or nodes and you have edges connecting them, and when we say that it is directed, so for example, you take, so there will be an arrow, So, the 1 to 2, you cannot go from 2 to 1 through this edge or the arc, we call it the arc, right. Similarly, you have like this, then you may have this, and you may have 4, and for example this. So, this is the directed graph where the nodes are 1, 2, 3, 4, and the edges you will write down as 1, 2. There can be many ways of writing down the edges. I do it through the starting node and the ending node. So, this is, for example, this edge I will write as 1, 2, right, and similarly you have the edges 1, 3. So, your E consists of 1, 2, 1, comma 3, then you have 3, comma 2, right, and then you have 2, comma 4, right, and you have 4, comma 3. So, this is your set E, right. So, therefore, a graph would be denoted as a given set of nodes and given set of edges or arcs connecting the nodes. So, this is a directed graph. That means there is a direction from in which you can go from 1 to 2 and so on, right. And then you have weights attached to the edges, That means you have weight Cij, right, ij belonging to E. So, for every edge you have a weight, and we are considering the case when the weights are non-negative, because the formulation and the application of this primal dual will be straightforward. Of course, you can handle other situations also, but so weights attached to the edges are this, right. Now, your feasible set F is set of all the directed paths from a distinguished node, you can say from a given node S belonging to V, sure, and from a given node S to a given node T also belonging to V. So, this is a feasible set, all directed paths. For example, here a directed path can be 1, 2, 4, right, then it can be 1, 3, 2, 4, right, if my distinguished nodes are 1 and 4, right, then all possible directed paths would be. So, you have to specify S and T right in the beginning as to what is the pair of nodes through which you want a directed path. Once you specify S and T, then the directed paths are 1 to 4, for example, 1, 3, 2, 4, right, then that is it. So, in this case you have only 2 paths, but if you choose the edges as 1 and 3, then you will have 1 to 3, you may have 1, 2, 4, 3, and so on. This is a small graph, right. So, this is a feasible set. Now, then I can also say that this is all P, all paths. Let me denote this, right. Then what is your problem? The problem is, so the shortest path problem is minimize summation Cij, where ij belongs to P, right, and for all P belonging to F. This would be a concise formulation of the problem. So, that means we are adding up for any directed path, add up the weights of the edges which make up the path, right, ij is in P. Then okay, if you want to be more rigorous, I should have defined, say for example, I said that this is a path P, which can this is actually would be so here I can say that P is a sequence of edges, right, connecting is a sequence of edges connecting S and T, nodes S and T, right, whichever view. So, there will be a sequence of edges, for example, here from 1 to 4, then 1, 2, 2, 4. This is a path, and the edges that make up the path are 1, 2 and 2, 4. So, for the weight of this path, it will be C12 plus C24, right, and so you have all possible paths here, and then you want to choose the one which has minimum weight. So, this is your shortest path problem, and of course, this is one of them which has been solved quite efficiently, and but the idea behind almost all algorithms for Cij non-negative is some way of some modification of the primal dual algorithm. I will show you a straightforward application of the primal dual here. So, it is important while defining the shortest path problem that we should say that the problem is feasible, and that means that there should be a directed path from S to T. It should exist, right. Also, when I am talking of the rank of the node arc incidence matrix and so on, then the underlying assumption is that the graph is connected, which means that there is a path and not necessarily a directed path which exists between any two pairs of nodes. So, this underlying assumption then makes the other results valid, and so one should have, I should have pointed that out. Okay. So, let us formulate this as a linear programming problem. Formulate SPP as a linear programming problem. Right. So, what we will say define here is as, say for example, yes. Now, so that means you have to understand what a path would mean, or how would you restrict your choice of the variables in such a way that you have a path. So, for example, I will first define my variable xij to be 1 if ij belongs to P and 0 otherwise, right. If I do this, then for example, consider node S, the starting node, right, consider node S. Then from node S, any path would consist of one of the edges which are leaving S, right. So, therefore, the constraint for node S would be summation x s j summation over j. So, I do not know, whatever the arcs which are connecting it should be equal to 1, because only one arc must leave the node S, right. Then for any intermediate node on the path, there will be one node which enters it and another node which an edge will enter the node and an edge will leave the node, right. Because if I reach up to I, my objective is to go from S to T. So, any intermediate node, if I reach an intermediate node, I must leave it, and therefore, we can say that summation xij this minus summation xji this should be 0, as long as I is not equal to S and T. For all other nodes, I must have xij, that means this is the node which are leaving node I, this, and then, so if in case this is 1, then this must be also 1. If this is 0, then this is 0, or either way, if this is 1, then this must be 1. That means, if one arc has entered I, then one arc must also leave I, right, that is clear. And finally, x summation, yes, summation x j t, summation over j must be equal to minus 1. That means, the last node T, only path must enter the node T. There is no question of leaving the node T, because once you have reached node T, you are done. You have a path connecting S and T. Okay. And then you have your xij equal to 0, 1. So, this is not a linear programming formulation, because for all ij belonging to E, because I am forcing the variables to take the value 0, 1. So, the constraints have been written out here when I am trying to formulate this as a linear programming problem, the shortest path problem. These are the constraints, but you see that here we require the variables to be integer valued. So, therefore, this is not in the strict sense a linear programming formulation. So, I will later on show you that we can do away with these constraints. Okay. Now, the objective function also has to be written down. That means, we will be adding up the weights of a path So, but right now these are your flow conservation, or you can say that these are the constraints will ensure that you have a path as a feasible solution, because this says that at least one arc will leave node S, and then intermediate nodes I not equal to S comma T. If an arc enters a node, it must also leave it, and finally only one arc should enter node T. So, these are the constraints, and we can, to write the linear programming formulation, let me now write down the node arc incidence matrix. Node arc incidence matrix. Okay, so this is where the rows are rows represent the nodes and columns represent the edges or the arcs. I mean, see, yeah, mostly people in the directed scenario, people prefer to use arcs instead of edges, but I have been using the word edge, doesn't matter, right. So, here for example, for this graph, when you write down the node arc incidence matrix, it will look like this. So, here you have node 1, 2, 3 and 4, and the edges that you have are 1, 2, 1, 3, right, 3, 2, 3, 2 and 3, 4, 3, 2 and 2, 4, 2, 4 and 4, 4, 3. Okay. So, for 1, 2, for example, this is leaving node 1 and entering node 2. So, there will be a -1, 0, 0, right. Similarly, for this arc 1, 3, it will be a +1 here, 0, -1, 0. Then 3, 2, it is leaving node 3 and entering node 2. So, this will be 0, -1, 1, 0, right. And then 2, 4, it is going to be 0, 1, 0, -1, and 4, 3 will be 0, 0, -1, 1. So, this is your node arc incidence matrix. So, if you write it, you take this as the matrix A, the constraints here can be written as, and your right hand side vector B will be as 1, 0, 0 and then -1. Yeah. So, this is for node 1 and this is for node 4, and then for 3 and 4, 2 and 3 it is 0, the right hand side vector. So, I can now write the linear programming formulation for the SPP with the objective function and everything, because the weights are. So, for this particular problem, the formulation will be, yeah. So, now you can say that minimize z equal to summation Cij Xij, ij belonging to your edge set E, subject to Ax equal to B. And right now, I am still saying that it is your this thing is ij is 0 or 1 for all ij belonging to E. This is my formulation. And now, what I want to show is that, first of all, of course, let us look at the matrix A. So, what we are saying is that rank A is n minus 1. So, let me begin with all the properties of A, and then we will come back and show you that I can remove these integer constraints. So, the idea here is, you see, if you add up all these constraints, the right hand side will become 0, both sides, because 1 minus 1, 1 plus minus 1 is 0. And here you see, if you have an Sj here, xsj, then for the node j, xsj will appear with a minus sign. So, this will cancel out, and so in pairs these variables will cancel out, and so you will have 0, 0 on either side. So, when you add up all the constraints, I have written this is as 1. So, add up all the constraints. So, add up all the constraints in 1, add up all the constraints in 1, to obtain the 0 row. Okay. So, or you can look at the matrix here, just add, see, because every column has 2 non-zero entries and one is +1, the other one is -1. So, if you add up all the rows here, they add up to the 0 0 row, and so you know that the rank of the matrix cannot be n, it has to be less than or equal to n minus 1, and then to actually show that it is n minus 1 will require a little extra work. So, you have to take my word for it at the rank. So, therefore, what I have shown you is that the rank cannot be n. So, but the rank is n minus 1, okay, and that is what we do. So, therefore, that means one constraint can always be expressed as a linear combination of the remaining constraints, or that means I can decide that the last row can always be written as a linear combination of the first 3 rows here. So, therefore, and that you can see why, because if you add up just these constraints, that means add up the constraints. So, add up, yeah, which is again a repetition, because if all adding up all the constraints gives you the 0 row, then that means one constraint can be written as a linear combination of the others. But see, add up the constraint summation x s j summation over j equal to 1 and summation x I j summation j over j minus x j I summation over j is equal to 0, right. Just add up these, leave out the last one. So, then again from here you see that all these will cancel out, because for you you don't have the constraint for the tth node. So, you will be left out with xjt, right, because the variable for the node t, the arc which is coming into t, it is leaving the node j. So, therefore, it will have a plus sign. So, when you add up these constraints, you will be left out with xjt, and the right hand side is 1, right. So, this adding up this implies that summation xjt is equal to 1 summation over j. So, we just multiply it by minus sign, because we want to keep this intact. Anyway, so therefore, what we will decide is that we can always we can forget about the last constraint, because it is implied by the remaining ones. And also what we want to say is that here, yes, another property of matrix A is that the basic feasible solutions. So, basic feasible solutions of Ax equal to b are 0 1 valued. This is a property which is also known as unimodularity property. Again, in this course we will not be able to actually show you that it is this holds, why this holds. So, since this property is already there, and linear programming formulation only works with basic feasible solutions, therefore, we do not need to explicitly use the constraints xij equal to 0 1, right. So, therefore, I can remove these constraints and I can say that this is just greater than or equal to 0. So, this would be a linear programming formulation for the SPP, and you can also have a nice interpretation of the complementarity slackness condition. So, of course, you will have to write. So, if you look at the dual, nice structure. So, I will just write the dual here, because you see that now the columns have a very simple structure. So, here the dual would be, if I associate the variables pi I. So, this will be maximize pi s subject to pi I minus pi j, and this is a maximization problem. Here you have equality constraints. So, therefore, and this is no negativity. So, this is less than or equal to Cij, and your pi I are unrestricted, and I will also use the convention of keeping pi t equal to 0, because we are going to not explicitly mention the last constraint. Okay. So, this is your dual problem, and you see it has a nice structure, and later on we will be able to make use of this special structure here. And then a quick interpretation of the complementarity slackness conditions. What it says is that if Xij is 1, that means if it figures in the path, this implies that your pi I minus pi j is equal to Cij, right, that the dual constraint will be satisfied as equality. And if pi I minus pi j is strictly less than Cij, this implies that Xij has to be 0. That means the corresponding arc will not figure in the optimal, in the shortest path. So, and later on we will show you many more interesting interpretations and how the algorithms are developed using these formulations. Okay.